Hi, hello everyone. Welcome back to my channel RL Lab. So we were discussing about the real numbers of 10th class. We have completed first exercise, right? So today we will try to see second and third exercise. Okay. So exercise 1.2. So what is the first problem? First problem is express each of the following numbers as a product of its primes. Already we have know that how to find it. So out of 4 problems, I will try to discuss one problem. First bit, third one, 3825. First bit, third one, 3825. Simply what we have to do is we need to find out the product of its primes. Just product of its primes you need to find. Just you factorize this 3825 as product of primes. So here 5 table, if you take, when it is the unit digit number, definitely it goes in 5 table first, right? So let us start with 5 table. 5 7 is 35. What is left? 32. 5 6 is 32. 25. 5 5 is 25. Right? Next again it goes in 5 table. 5 1 is 5. 26. 5 5 is 25. 5 3 is 15. So I think it goes in 3 table. Only with the prime numbers you have to do. So 3 5 is 15. 3 1 is 3. 3 1 is 3 1 is 3. 3 7 is 21. 17 is a prime number. You can stop at this point of. So 3825 as product of primes means 3825 is equal to, so if you write it in order, 3 into 3 into 5 into 5 into 17, right? 3 into 3 into 5 into 5 into 17, order I have written, right? So the product of primes of 3825 is this one, 3 into 3 into 5 into 5 into 17. If you write this is in exponential form also, what do you get here? 3 square into 5 square into 17. So I think this is clear to everybody, right? So remaining 3 sums are there. In the same way you have to do it, right? Right? Next problem. Next problem is find the LCM and HCF of the following integers by the prime factorization method. So find the following LCM and HCF of the following integers by prime factorization method. While finding LCM and HCF, I have discussed about 3 methods. One is listing the factors. For LCM, listing the multiples and division method and general ledger method, right? And here prime factorization method. Next, HCF also prime factorization method, factors method and division method. There will be three methods for finding HCF and LCM. I have discussed here in the number system, right? You can go through in my videos. You will come to know. So I'll directly enter into this. Find the HCF and LCM of the following numbers by using prime factorization method. There are 5 sums. So I'll try to discuss one sum, 1 or 2 sums. 72 and 108 is there. So in this case also you need to do just a prime factorization of each of the given number. Let's do it first. 2 1s are 2 3s are 2 3s are 6, 2 6 are 12, 2 18s are 2 9s are 3 1s are 3 3s are, right? So next 108. 108 they also same. 2 table it goes. 2 5s are 10, 2 4s are 8, 2 2s are 2 7s are. Again it goes in 3 table. 3 9s are 3 3s are. So now 72, therefore 72 can be written as exponential form. I am writing 2 cube into 3 square and 108 in exponential form 2 square into 3 cube, right? So this is exponential form. While finding LCM or HCF, you need to follow 2 steps. Those are, you have 2 formulae. LCM of first HCF, let us see. HCF of 72 and 108. The formula is product of smallest powers of Product of smallest powers of common prime factor. Each common prime factor. What is that? Each common prime factor. Okay. So what is each common prime factor here? First, common prime factor you have to check. 2 and 3 are common factor both in both 72 and 108. So first you write them as product and you assign the smallest powers. What do you have to do? Smallest powers into 2 cube 2 square. What is the smallest power? 2 square is smallest power. Here 3 square 3 cube. What is the smallest power? 3 square. So 2 square into 3 square, 4 into 9, which is equal to 36 is your answer. HCF of 72 and 108. Similarly, LCM. LCM is nothing but LCM of 72 and 108 is product of greatest powers. Product of greatest powers of each prime factor. Here no common, only each prime factor. Let's see here. How many factors are there? Here only common prime factors are there. There is no other factor which is not common, not present here. So 2 and 3 you write and assign the highest power. I think in both the cases 3 is assigned, 3 is the highest power. So 2 cube into 3 cube. 8 into 27. 27 8s are 8 7 56, 8 2 the 16 plus 5 216, right? So this is what your LCM. Clear? This is a prime factorization of finding HCF and LCM. This 72 and 108. If there are one more number exists, also same procedure you need to follow. Same 72 108. Suppose something 156 you are getting. 156 also you try to express in the form of prime factors, and then you write here down. Same all the three common means here first you have to check all the three numbers what is common prime factor. Then that only you write. If one exists, only 2 exists in common, all the three, you write only 2. If 3 exists, only 3. If both 2 and 3 exist, you write all them. If anything is not there in common for all the 3 numbers, then you have to take it as 1. 1 is the highest common factor. Clear? Why? Because if no factor is common, then they are called co-primes. Clear? So if nothing is common, then simply HCF of those will be equal to the 1. Okay, same LCM also highest power you need to write. Here each prime factor should be involved. If some other factor, suppose 5 is there in this 72 and the remaining 2 or remaining 1, 5 is not present also, you have to write here 5 extra. Each prime factor. Why? Because here each prime factor, here each common prime factor. Here you have to take only common, here only each prime factor, right? This is about the second bit. Next is third one. What is this third bit? Let us see. Right. Third question. Check whether 6 power n can end with digit 0 for any natural number. Right, let us see the solution. 6 power n. In general, there are two ways to find this. 6 power n can be written as 2 into 3 whole to the power n. Right? And here, clearly, in order to end with the digit 0, any number to the power natural number can end with the digit 0 means the prime factorization of that particular number should contain 2 and 5 as their factors. 2 and 5 as this particular number factors should be factors. But here if you see for 6 there exists only 2 but not 5. If both present only, that particular something to the power natural number will end with the digit 0, otherwise it will not end with the digit 0. Clearly this will not end with the digit 0. That you have to write in the form of statements, right? Clearly the prime factorization, in order you have to mention that in order to end 6 power n with the digit 0, it should contain 2 and 5 as its factors. Apart from 2 and 5, other factor exists also, no problem. But those two should be present. But here 5 is not present in the prime factorization. Five is not present in the prime factorization. So therefore 6 power n cannot end with the digit 0 for any natural number, for any n belongs to n. Clear? For any natural number n. In other way, 6 to the power natural number. See, if you take out this, 6 power 1 is equal to 6, 6 power 2 is equal to 36, 6 power 3 is equal to 216, 6 power 4 is equal to 1296. You take out like this, any power, if 6 is raised to the power any natural number, it will always end with the digit 0. No, sorry, it will always end with the digit 6. 6 to the power any natural, 6 is raised to the power any natural number is always end with the digit 6, clearly. From this also we can conclude that 6 power n cannot end with the digit 0, cannot end with the digit 0. 6 power n will end with only 6. But this problem is also there. I think last problem. What is the last digit of 6 power n? 6 power 100. What is the last digit? Sixth problem is there. What is the last digit of 6 to the power 100? Whatever may be the power, whatever may be the natural number of 6 to the power natural number, it ends with 6 only. Because the cycle, see, you can observe this side, 6 to the powers always ends with the 6 only. So 6 to the power 100 is also will ends with the 6. Like this you can write and you can say this answer also. Okay? I will not repeat again this 6. 6 to the power 100. So what is the last digit of 6 to the power 100? Is always 6 only. Clear? Right. Next problem. Fourth problem. Fourth problem. 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Why these and these numbers are composite numbers? Why this and this are composite numbers? What is meant by composite number definition? Already in the number system I have discussed about the composite number and prime number definitions also. Please you can go through that video if you have any doubt about the composite number, right? Now composite number is nothing but minimum. A natural number should have minimum 3 factors. A natural number should have minimum 3 factors. Then only it is called a composite number. See, 6. 6 is nothing but 3 into 2 I am writing. If any number is expressed as a product of 2 numbers other than 1. Suppose 5 is there. 5 can be expressed as 5 into 1. What I am saying here, any number should express as a product of 2 numbers other than 1. Like this, it cannot be accepted. Why? Because 5 is expressed as 5 into 1. What I am saying, it should not express as a product of 2 numbers other than 1. It should not include 1 in that. So 6 is expressed as 3 into 2. Other 1 is not involved in this. So this type of numbers are composite numbers, but not this. Clear? So now I will try to express this as something. Check out here, this 7 into 11 into 13 plus 13. Here 13 is common. This total is one number, no? 13 is common. Here 7 into 11 plus 1. Whatever may be this value, I do not know it. 13k, I am making it as k. Where k is equal to 7 into 11 plus 1. Let us say 77 and 78, whatever it may be. Now this whole number I am expressing as product. 13 into, no, this is 13 into k, no? Yes or no? So I am expressing as product of 2 numbers. 13 is one factor and k is also one of the factor. And anyhow 1 is also becomes a one factor for this number. But because 1 is a factor of every number. Are you following? 1 is a factor of every number. and 13 is also a factor and k is also a factor of this number, then obviously it will have minimum 3 factors. So it is a composite number. Can I conclude like this? In the similar way, here also you observe here. You take out 5 common in this. 7 into 6 into 4 into 3 into 2 into 1 plus 1. Right? I have taken this sum 5 into L. I will take this as where L is equal to 7 into 6 into 4 into 3 into 2 into 1 plus 1. I am taking this total number as sum L. Now I have expressed this also in the form of product of two numbers, 5 and another number, but not 1, isn't it? So can I conclude that this is also a composite number? Because it has expressed it as a product of 2 factors other than 1. Clear? This is about fourth problem. I hope this is understood. Right? Now last problem is also same problem. You can solve it. How will you show that 17 into 11 into 2, 17 into 11 into 2 plus 17 into 11 into 5, 17 into 11 into 5. How you show that this is composite number? This total is a composite number. Explain. Same procedure you have to follow. Here what is common? 17 into 11 is common. Take out 2 plus 5. So 17 into 11 into 7. Clearly that is a product of 3 numbers. So obviously that is a composite number. Clear? This is about exercise 1.2. Clear?